Hey folks, good evening. Hope you all can hear me. Uh, it would be nice to have a confirmation. If you can hear me and if you can see the screen, it would be nice if one of you can confirm. Okay, seems like it is fine. Cool. So today we are going to basically start on segment trees. I hope you all can hear me, like all who have joined very recently. Can you please confirm? If I am clearly audible and if the screen is visible, you can see me writing the topic. Approach and implementation. Hi, approach and implementation. So anyway, one of the most standard topics which we all consider as the shifting point, transition point from intermediate topics to advanced topics is segmentaries. Uh, Hi, good evening. So this is the topic that we are going to discuss today with kind of a beginner level perspective. We are going to see from the basics, from scratch, how segmentaries do come, where they become important, why without them we can't sometimes do the things that they help us in doing. This is what we'll be discussing today, and we'll be starting around in 4 or 5 minutes. Starting at I think 5:36 p.m. Till then, whatever questions you have, you can ask regarding previous classes or regarding today, regarding any content that we'll be covering today. Whatever questions you may have, you can ask now. So, while we study this topic, the important point of focus shall be the approach. How to approach a question of segmentaries, how to approach those domain of questions which segmentaries help in addressing. And then we'll look at the implementation, and our focus shall be to see what is common in all these implementations and how we can transition ourselves from one problem to another, keeping most of the implementation same and identifying only the places where they are different. We'll only try to focus on the differences and see how the rest of the coding can be made easier. How difficult as compared to binary tree? How much time for this class? Around 2 hours. It should not be more than 2 hours. Around 2 hours. So how difficult? It's this is such a topic. Okay, with respect to binary trees, what I can say is that definitely the lines of code will be a bit more, but conceptually there is not a lot more. You just have to understand why the complexities and all are helping you. Okay, nice to know, Pushpak. So where were I? Yeah. So after that, only the complexity parts will be much more intrigued and involved. You'll feel excited over there, and then the only difference between binary tree and segment tree probably is that segment tree helps us in solving much difficult problems. But conceptually, it is not that difficult. Like if you know binary trees, then today's class will be a very good platform for you to transition comfortably to segment trees. So this is the third topic that we are covering in this series. Before this, we have covered two sessions on tries. In the first session, I talked on character tries. In the second session, I have talked on binary tries and also revised character tries. So from these two sessions, there are a lot of classical problems that you all can find out. They are definitely not a prerequisite for today's class, but just if you feel that you want to catch up on those topics, you want to see how to like solve different problems on those topics, you can visit those lectures. They were also created with beginner perspective in mind, but there might be some certain things you can gain from there, so you can look at the recordings later on. And today we are going to discuss on segmentaries, and this is the first class on segmentaries, so there is absolutely no prerequisite for this course, so far as my previous sessions are concerned. Cool. Any questions, like, keep on throwing. I'd be happy to answer in these 1 or 2 minutes. We'll be starting at 5:36. So till then you can keep the questions coming. This is basically the agenda. I would talk on the basics of segment tree. I would delve deep into the time complexity analysis part. Okay, so this is 120 minutes, I think I had mentioned. I'd be covering the basics of segment tree. I'd delve into the time complexity analysis. I'll go through some examples, some problems, of which they'll mostly be classical problems. I won't give computer programming problems today, but you will find them easily applicable in various computer programming problems. Does this session, not today's session, but we can cover that tomorrow. Tomorrow I think I'll be leaving lazy segment trees for tomorrow. I think today's class won't allow to cover lazy segment trees. If time permits, we'll cover lazy today only. Else we'll cover lazy tomorrow. And after that, we can cover 2D segment trees. So today we'll basically focus on solving problems on segment trees, on the basic intuition of segment trees. And there are two advanced concepts that I'll prefer to cover, which is coordinate compression. That is only a very small supplement to segment trees, coordinate compression, and sparse segment trees. Once these are done, you can actually address similar kind of problems on a wider domain of constraints. We'll actually observe that. But this is pretty much the agenda for today. If you have any questions, you can ask. Is it the same data structure which is useful in queries question? Exactly. Cool. So let's move ahead. If you have any question, you can ask, else we'll start with the first part of the topic. So this is basically the problem that we sit with, or the kind of problem that we notice at many places. You are given some n positive numbers, or maybe n numbers in an array, or an array of n numbers, and then you are given q queries. Each query is of this kind. The first kind is a kind of update, where you say, first query is something like this, where you say that go to a particular index I and change its value to a particular value x. What we basically mean is that, suppose the array is A, what we basically mean is AI has to be changed to x immediately after this operation. And the second kind of operation is something like this. It comes as a tuple of 4 integers in this case, I think, L and R. So 2LR. What this specifies is, it asks from you the sum of the numbers from the lth index to rth index of the array. So you basically have to return the sum of AI, where I ranges from L to R. Got it? These are the two kinds of queries. So one sample thing, suppose I give you that this is your array, 3, 1, 2, 4, 5. And these are the operations. The q queries, q is equal to 3 queries. And suppose I tell you these are the queries: 2, 0, 3, 1, 1, 2, 2, 0, 3. So basically 2, 0, 3 is going to return you the sum of the values from the indices 0 to 3. So it is basically 10. Over here there is no returning operation, but what it requires to do is, it has to convert this index, the value at this index, to 2. So it will convert this value to 2. Next we say 203, that means we again want in the same range, but now the value has increased. Now we will say that now the sum is 11. Make sense? So according to the classical application of this kind of problems, n ranges to around 10 to the power 5. Let us assume for this question that n ranges to 10 to the power 5. We have q ranging to 10 to the power again 10 to the power 5. Alright, and now you have to find this out. Basically you have to solve the problem so that it passes in 1 second, and that's what is given to you. Now how will you proceed? Any questions regarding the problem statement? These are the three queries. You are basically given these three lines. You'll be given the value of query, that is q. Three queries means three lines will follow. Every line will tell you how this operation is going to be. Now think of certain approaches. First of all, we have the brute force approach. So what is the brute force approach? First of all, is there any problem or is there any confusion regarding any of the queries that I've mentioned? This is basically an update operation where we are saying update a certain index. This is called basically a point update. Why? Because we are updating the value at a certain point. The update in the array is taking place at a certain point. And a difference to this we'll be observing tomorrow, where we'll be working on range updates. But till now it is good to focus on only one part, that is point update. The next part is what talks about is range query. What this means is we are querying the information over a certain range. That is why we'll call it an instance of range query. So the first query is range point update, and the second query is a range query. These are the two things we have to address. Now we know that the easiest part is simulate the entire process. Take an array and go on changing. If it asks you the value, return the value. If it asks you the sum, then compute the sum and return it. Hi Hitesh. So this is basically the problem we are discussing. This is the problem which you have to solve. There are two kinds of queries. These queries can come alternately or in any order basically. You can have some point updates, then some range queries, then some point updates. This is basically the order. And whenever there is a range query, you need to return what is the value for it. Like what is the summation of values within that range. Now the thing is that when you return the value for this range query, you need to take into consideration whatever updates you have done before that. And there lies the crux of this problem. The thing is that when you're querying over a range, suppose this is the array and you're querying over this kind of a range, suppose some updates have taken place. So in order to account for those updates, this computation over this range can become quite tricky. And this is the entire crux of this problem. Think about, you're just using an array. If you're just using an array, this update operation is very easy, right? You can just go to an index and you can update it. You can say that, okay, I'll change it. But next time when I'll ask you the sum over a certain range, for whatever updates you have made, you need to find out whether all those updates lie within this range, or some of them lie in this range, some of them lie outside this range, and so on. There are many questions that follow. And if you use a basic approach that, okay, I'll compute the sum. I'll compute the sum one by one. Whenever it gives me L to R, I will sit at L, I'll go up to R, and I'll go on adding the things, whatever are there. This is the basic approach, wherein we can say that the time complexity of this range query will turn out to be order R minus L plus 1, right? So R minus L plus 1 can rise up to n. It can be n by 2 and n by 3, whatever, that is basically order n. So what I just mentioned is an approach which uses the basic arrays. Array, and over there we are just going to do a kind of brute force. We know the update operation is pretty optimized. The update operation will be just go to the index, change it. So this is an order 1 operation. And then when we have to query in a certain range, the requirement is to move from R minus L, basically L to R, so R minus L plus 1, which is actually order n, right? So from here, what turns out is that if I have 10 to the power 5 by 2, basically q by 2 updates and q by 2 queries. Q is the total number of queries, right? So q by 2, suppose half are basically range queries. So if I have these many queries, what can I say? This will turn out to be 10 to the power 5 by 2, and n value is also 10 to the power 5. What this means basically is that it crosses 10 to the power 9, thereby making this totally infeasible to be computed in 1 second. And hence, keeping just this range query in mind, this brute force is not apt for these constraints. Any questions till now? Any questions till now? Is it clear how I have basically computed it? I'm basically doing brute force. So is it clear that okay, I think no means basically you don't have any doubt. If you have any doubt, you can specify any part that I need to repeat. Cool. So the first thing that comes to mind immediately after this, that this is what we need to change. You should speak slower. Sometimes you go to verb speed talking. Okay. By the way, I'm not sure. Are you all comfortable in Hindi? Or should I continue in English only? Because yesterday's experience was that students found it a bit easier, or maybe they were able to connect well in Hindi. So should I stick to English, or both are fine? Okay, great. It's good that you have mentioned at this point. Else sometimes it actually becomes problematic later on. So cool. I'll be speaking in English. Even if some part I mention in Hindi, rest assured that that part I have definitely mentioned in English. So I'll be sometimes mentioning in both the languages. I'll make sure that I have mentioned at least once in English. Okay. So यहाँ पे कुछ ऐसा है. I'm just mentioning the same thing in Hindi. What we are basically doing is, हम एक एरे में यही बोल रहे हैं कि जब तुम्हें अपडेट करना है तो एक वैल्यू में जाके उस इंडेक्स में जाके डायरेक्टली चेंज कर दो, और अगर तुम्हें एक रेंज में निकालना है सम, तो उस रेंज में ऐसी बेसिकली कंप्यूट करो कि वहाँ पे मतलब अब फाइनल वैल्यूज़, करंट जो वैल्यूज़ है उनको लेके सम क्या आ रहा है. तो इसमें ये दिख रहा है कि अपडेट वाला ऑपरेशन काफ़ी ऑप्टिमाइज्ड है, ऑर्डर 1 में हो जा रहा है, बट रेंज सम वाला ऑपरेशन काफ़ी टाइम ले रहा है, वो ऑर्डर n ले रहा है पर क्वेरी. व्हाट दिस बेसिकली मीन्स इज दैट कि वो हमारा बॉटलनेक बन जा रहा है. अगर हम q टाइम्स वो चीज़ करेंगे या q/2 टाइम्स, तो ये काफ़ी ज़्यादा हो जाएगा, 1 सेकंड में नहीं हो पाएगा. Is it 10 to the power 8 or 10 to the power 9 operations per second? The limit, yeah, it is actually 10 to the power 8. The operations need to be less than equal to 10 to the power 8, or you can say less than equal to 2 into 10 to the power 8. वो भी पास हो जाता है. That also passes. But like, yeah, I just mentioned that this is crossing 10 to the power 9. Yeah, this is crossing 10 to the power 9. That is what I mentioned. So since it is crossing 10 to the power 9, it is nowhere possible, right? That is what I mentioned. Cool. So coming back to the topic, we want to optimize the range query part. So the question is that one approach is that we can combine a certain set of queries. We can say that, okay, maybe if there are 2-3 range queries successively being asked, then all of them we can take together, and we can calculate for all of them together. So when we start from one and to the next, like we can figure out something. But if they alternately come, if some update comes, then a query comes, then some update comes, and there is a lot of permutation over this, this can easily get violated. This, like, we cannot directly apply this kind of an approach. And also it requires a bit of cleverness, because L and R both vary. Not only that you can sort the queries based on R, but L also varies, and there is a different algorithm that helps in dealing with such kind of situations. You might have heard about Moore's algorithm. We will not discuss that here, but if you are like at any other point of time, we may discuss. Moore's algorithm slightly works in that kind of a manner, that you combine certain queries, you move from one part, you say that, okay, I'll start from L equal to R equal to 1, and then you gradually extend it rightwards, and then you also change the left index gradually, or the right index gradually. There is a cost associated with each of these operations, but in a calculative manner, we can keep it down to n root n or n plus q root n, something like that. Okay, but anyway, we'll totally like keep that aside. That is not the agenda. The current agenda is that we want to improve this query part. So the very well-known method of improving the summation part, I want you to answer me that what is the summation of indices or summation of values from ith index to jth index. So what can be the approach? What is the very popular approach? Whenever there are so many queries and you have an array and you have to find out the sum of any subarray at any moment, what is the very common approach that comes to mind? There is one implementation of basic arrays which helps you, and that is prefix sums, right? Exactly. So we can apply prefix sum, and what turns out? So whenever I ensure that at any point of time all the prefix sums are stored, basically in an array, every ith index contains the sum of all the elements from the beginning to the end in the updated manner. So if I have changed something over here, then that should reflect over here also, that okay, the sum up to here has changed. If I have this kind of a setting, if I have the prefix sums all in place, what advantage I'm gaining is that now if I ask the range query, if I ask that okay, I want to find sum of L to R, what I basically have to ask is find me the prefix sum of R minus prefix sum of L minus 1. That's it. So what this indicates is, I think what Ivan actually meant is prefix of I minus, prefix of J minus prefix of I minus 1. Yeah, Hitesh should record it. So that's good. But now, so we have actually found out that since both are pre-calculated, ये दोनों ही pre-calculated है, so we can calculate this in order one time. In order one time, we can address the second kind of query. But the first kind of query, which was about updating one element, has now to be considered, is now left to be considered. So let us see, if we update this element, which is at a certain index L, what is the time complexity for making the update? Suppose this is the prefix sum array, and we are changing this element in the original array. So what can we say? All these prefix sums are going to change. Can you see that? So for this example, where did I take the example? Okay, over here, 31245. Can you see that initially my prefix sum is something like this? I have 3 over here, then I have 4, 3 plus 1, then 6, then 6 plus 4, 10, and then 10 plus 5, 15. Now if I say I want to change the first element, what shall happen? Basically this prefix sum is going to increase by 1, and similarly all these prefix sums are going to increase by 1. What this basically means is that now the cost of increment in this data structure of prefix sum that we are maintaining is not order 1, this is order n. We have to iterate through all the elements in the worst case. What that basically means is we have improved the first kind of operation, I think the second kind of operation, query part, range query part, we have improved to order 1, but the update part we have improved, we have actually we are consuming order n, which means this is not again worth it because there can be q by too many updates. Okay, how the formula came? The formula basically means that prefix of R means the sum of the first R elements. So every time this data structure is going to store that up to a particular index, what is the sum of all the elements. So what can I say? If I have to find from L to R, what can I say? In prefix of R, I will have the sum of all the elements from 0 to R, and in prefix of L minus 1, I'll have the sum of all the elements from 0 to L minus 1. So from 0 to R, I have all the elements, their sum, and from 0 to L minus 1, I have all the elements, basically their sum. If I subtract it, shall I get the remaining elements, which I basically want? So this is like I'm taking a greater subset and then I'm subtracting the part which is not necessary, not required for our case. Make sense? Hitesh? I'm sorry, Amit? So what prefix means is that summation from the first index to that index. So anyway, I think it makes sense. Yeah. Okay. So now coming to the next part, how can we improve it? Now we want to improve both the things, and it turns out that they are kind of trade-offs. If we try to improve one, The other part may become problematic. So let us proceed and see how we can try using a divide and conquer approach to solve this. Let us suppose that we have 8 elements. We have 8 elements, something like this: 3, 2, 4, 1, 4, 2, 5, 3. These are 8 elements, and we are doing something like this. We are maintaining, so these are our let us write something like this. These are 8 elements, totally independent elements that we are maintaining. Yeah, we can use Fenwick tree, but today we'll discuss only on segment trees. We won't delve into Fenwick trees. So we have these values: 3, 2, 4, 1, 4, 2, 5, 3. And what do we know? These are the indices: 0, 1, 2, 3, 4, 5, 6. The approach that we will adopt over here is that combine them in pairs. Combine these values, these nodes, in pairs. What you get is a sum of 5. Over here you get a sum of 5. Over here you get a sum of 6. Over here you get a sum of 8. And when we are combining this, what we are having in mind is this stores the sum of these two indices. This stores the sum of these two indices, and so on, these two indices. Right? Now suppose we have to search for this particular range. What do we know? According to our first approach, how many operations or how many exact steps were required to sum up these elements? 6, right? 6 values had to be taken into consideration. Now let us come over here and let us see what is the situation over here. If I want the sum of these elements, how many elements do I really require? How many elements do I have to combine? I know that these two elements, I don't have to read them separately. I have already stored that over here. So I can directly use it. Similarly, I can directly use this particular node. Why? Because this accounts for these two places together. So all these indices are important to me, hence I can directly take them. And for this reason I can say that okay, come up to here, and for this come up to here, something like this. Now how to access it? Maybe that is again a tricky part, that how you can reach these nodes, but you can see that the combination part becomes quite easier for us, right? Now we know that the number of nodes that are important to us is at most n by 2. Make sense? It is at most n by 2. Suppose I suddenly ask that okay, I want this range now. What can you say? Now okay, I'll be taking this node, I'll be taking this node, and I'll be taking this node. Done. So from 5, this would require 5 operations. We have decreased to reading 3 nodes only. This is a direct decrease that we are doing, and this is basically something that we would be exploiting in the coming part of the lecture. Okay. So what is observation? Observation basically is that we are combining something and we are exploiting the part that okay, this particular part remembers its sum, so let us use it and let us not waste our time. The question arises, how can we update the things? In order to update the things, what is observation? If suppose I have to update this value, I should update in a manner so that after this, when I query for a certain range, the structure that I am forming is consistent. Later on when I query for it, it should tell me honestly that these are the values that I have in this range, right? So when I query or when I say that okay, update this particular value to something like 7, what will it say? I have to increase by 2, or maybe like I have to just change to 7. So reach this node, change to 7, move upwards, and we know that this value is also supposed to change. So we can say that 7 plus 3 is 10. These are the values. It takes only 2 operations. Can you see that it takes only 2 operations? It will take not the maximum, the number of operations will be exactly 2. So what do we know? That the number of updates will always be less than or equal to n by 2, or the number of nodes that we are considering for contributing to our, So for updating, or sorry, for querying, for basically finding out the sum, these are the number of nodes which we are adding. And for our update operation, this is the number of nodes that we are changing. Other nodes we don't have to visit at all. So this gives us an idea that we have actually kept both under our control. We have improved one without deproving the other two badly. And this brings the idea that what if we do this one step further? Why not we combine this even further? Shall that help us? This is what the question is. So till now, is everything clear? If the number is odd, then let's say we eliminate 3, then node will be 7. How to construct 3? Okay, good question. We'll then construct basically an empty node which we'll not consider for our reason. So that empty node, if it is a kind of this kind of a question, summation, we can keep that as 0. So all the last elements can be 0. We can basically take the nearest power of 2. That won't, what do we know? If we convert n to the nearest power of 2, then it will definitely be less than equal to, like, if we convert to the nearest power of 2, it will definitely be less than equal to 2n, right? So the total number of elements that we are considering instead of the actual size of the array is less than equal to twice the array size. So it is not that bad. So this is basically like something that we can do. Just add some zeros over there. It doesn't matter. But yeah, we'll discuss this at length, that how we handle these cases and how this keeps the entire time complexity analysis consistent. That will be a very good part of the discussion. But before this, let us see how we can continue with this. Okay. Let us check from here. We have this array, and what I would now want is, let us do it a step further. So we can say we can connect these two. 5 plus 5, 10. So over here I am exploiting the property that it is a power of 2. Over here it is a power of 2. And hence what I can say is it will keep on joining till I get one node. So this is because of the assumption that I am taking that there is a power of 2, the number of leaves. Over here if we connect, this will basically be 14. And then if I connect it, we'll get something like 24. Right? This is how we can form the entire thing. Now let us see how it helps us. Now what do we know? If I have to find for this particular part, suppose from 2 to 2, what can I say? This 2 is again essential to me. This 2 is again essential to me. And for 4, 1, I can directly take this. And for 4, 2, I can directly take this. Again, the same kind of nodes. Suppose now I change my query to something like this. 4, 1, 4, 2, 5, 3. I want for this particular range. So what can I say? I'll come down. I can directly take this one because this represents the, I can directly take this one. This represents the range of 2 to 3. This is basically 2, 3, and then we have 4, 5, 6, 7. So I can directly take this one. So I can directly say 5 plus 14 equals to 19. Can you see that only using 2 nodes we can calculate over here? If the range of node overlap completely, then we take it directly. Otherwise, we go down the tree. Exactly. So this is basic intuition. This is not a kind of rule. This is basic intuition that we are applying. That what is the least number of steps we need to take to find out the sum. The idea is that when we come down, we face this 14. Why should we go down? We know that this represents the range of 4 to 7. So why should we go down? Why should we fetch these things separately? We know that the sum is over here. Why should we waste our time behind what is there beneath it? So this means that we can just focus on this part. We can just return this value. We don't have to read these parts. So this is basically what we do. And what this yields us, we have not yet formally proved it, why this is such a good approach, why the time complexity analysis is always in our favor. But the structure that I've formed, the tree kind of structure that I've formed, is the idea clear? Now if I have to update it, if suppose I have to change this node to 7, what will I do? I'll be changing this to 7. Due to changing this, what shall change? Which values shall change? Or can you say how many values shall change? 1, 2, 3, 4, 5, 6. How many values shall change if I update this value 5 to 7? How many nodes of this structure shall change? Great. So these are the nodes that changes. So what approach are we using? We know, yeah, Gaurav, it was just a question specific to this particular case. So basically, every node, if you have noticed, every node represents a range in the array. हर एक नोड पे मैं एक रेंज स्टोर कर रहा हूँ कि यहाँ से लेकर यहाँ तक क्या स्टोर होता है, कि मतलब सम कितना है इसका। और अगर मुझे देखना है कि नहीं, मुझे पूरा सम नहीं चाहिए, मुझे एक पार्ट का सम चाहिए, तब मैं उसके चिल्ड्रन के पास जाता हूँ। वेन एवर आई थिंक दैट ओके द एंटायर रेंज सम इज नॉट इम्पॉर्टेंट टू मी, आई विल रीच इट्स चिल्ड्रन एंड आई विल आस्क देम दैट ओके टेल मी व्हाट आर योर इंडिविजुअल वैल्यूज, बिकॉज वन ऑफ यू इज इम्पॉर्टेंट टू मी, द अदर वन इज नॉट होल्ली इम्पॉर्टेंट टू मी, समथिंग लाइक दैट. This is the internal complication, something like this. So what can we infer from here? That if we change a certain node, essentially हमें नीचे जाके चेंज करना पड़ रहा है, नीचे जाके हमें लाइक लीफ पार्ट में हमें चेंज करना पड़ रहा है. दिस इज वेयर द एरे सिट्स. एरे इधर बैठा हुआ है लास्ट लेवल में, और हम जैसे ऊपर जा रहे हैं, ये हमारा रिस्पॉन्सिबिलिटी है कि हम अपने अनसेस्टर्स को चेंज करते जाए, बिकॉज हम उनके अंदर लाई करते हैं. एंड दिस इज ऑल्सो वेरी इंपॉर्टेंट ऑब्जर्वेशन कि ये जो चीज़ है, इसको अगर हम मान लीजिए इसी को अपडेट कर रहे हैं, इसको हम अपडेट कर रहे हैं, तो जो इसके एंसेस्टर नहीं है वो बिल्कुल भी अफेक्टेड नहीं होगा. लाइक दिस पार्ट, this node will never become affected by changing that particular 2. Why? Because इसके अंदर, इसके बेसिकली ये जो चीज़ है, इसका जो रेंज है, वो इसके इंडेक्स के साथ बिल्कुल ही डिसजॉइंट है, एंड इट मस्ट हैपन. इन अ सेगमेंट ट्री दिस इज़ अ वेरी इंपॉर्टेंट थिंग दैट जो भी लाइक अगर दोनों नोड्स को हम ले, जो दोनों एक दूसरे के एंसेस्टर नहीं है या फिर डिसेंडेंट नहीं है, if one node is neither the ancestor of the other node nor the descendant of the other node, we can say that their ranges, the ranges that they are depicting, will be totally disjoint. Okay, so I'm not writing these points, but these are important points to remember. You can note them down. Every node represents a range, and if two nodes are neither ancestors or descendants of each other, then their ranges are disjoint. They have no element, no index in common. Okay, so one update means we have to change only the ancestors, not the other nodes which are not the ancestors. And descendants का question नहीं आता है. The question of descendants doesn't come because we are changing one element, so its descendant is not defined. There are no descendants of these last level elements. Okay, hope this point makes sense, else you can pitch up a question. So what I basically wanted to show is that we have now eased, though we have not proved it, we have eased the process of summing up without compromising the process of updating. Now, before moving into the time complexity, it would be nice to also make sure we also address the case of trie size or array size, which is not a power of 2. If array size is a power of 2, what will happen? If array size is 2 to the power k, what do we know? The depth of the trie is going to be, basically there will be k plus 1 levels, because what do we know? First level will have only one node, second level will have two nodes, third level will have 2 square, then finally and last level will have 2 to the power k. So we'll have k plus 1 levels. We can say maybe the depth is mentioned as k. This is the depth, right? Right. So this is basically the depth is k, the number of levels is k plus 1. This is basically 2 to the power 0. Okay. Hence, what can we say? What is the trie size? The trie size, we know that if the last level has 2 to the power k nodes and there is a complete binary tree, then what is the total number of nodes in this trie? Can everyone put down your, as per your own calculations, what is the total number of nodes in a trie which is built on an array of size 2 to the power k? There is, I think, a bit of lag and I can't do much about it, but if you answer fast, it shall be nice. What is the size of the trie means what is the number of nodes in the trie? 2 to the power k into k. Interesting. 2 to the power k plus 1 minus 1. Yeah. So Ivan and Tejas are actually right. From 2 to the power 0 to 2 to the power k, we have to add those elements. So if you do a simple GP operation, you get 2 to the power k plus 1 minus 1. And this is also an information you know from complete binary tree. You know in a complete binary tree, the number of internal nodes is 1 less than the number of external nodes. So the total number of nodes equals to twice the number of external nodes, twice the number of leaf nodes minus 1. So leaf nodes are basically the upper rounded value of half of the total number of nodes. This is basically n by 2. So what we can say, this is basically 2 to the power k plus 1 minus 1, not 2 to the power k into k. A better guess or a better approximation would have been 2 to the power k into 2. Okay, we have 2 to the power k into log n. Not really. Okay, I think you did an approximation. I understand. Okay. So the number of levels is k. That is why you did k into 2 to the power k. Okay, now I understand. Fine. Yeah. So now the thing is, we know that the trie size is 2 to the power k, and we know that this is equal to n. So what can we say this in terms of n? This is less than equal to 2n, right? So over here we can say that the trie size is not too much. It is less than equal to 2n. So if n is 10 to the power 5, then the size of the trie is also in our control. It is less than equal to 2n. Now let us also take the case of array size not equal to 2 to the power k. So we have some array size n, which we know something like this. It is less than equal to 2 to the power k, and it is greater than 2 to the power k minus 1. Okay. So for all of these, what I want to form is, I want to approximate this to 2 to the power k. So any value of n, any array size which lies in this range, I want to convert it to 2 to the power k. Okay, by appending zeros at the end. So now let us see in terms of n, what is the time complexity or what is the space complexity basically. So 2 to the power k, what do we know? What is the basically what is the sum going to be? What is the number of nodes going to be? It is going to be 2 to the power k plus 1 minus 1. Similarly, if we form this 2 to the power k plus 1 minus 1, what this basically means is less than equal to 2 to the power k plus 1. And 2 to the power k plus 1, what do we know? 2 to the power k minus 1 is less than n. So from here, can we say that 2 to the power k minus 1 multiplied by 4 is less than equal to 4n? And from here, can we say it is basically equal to 2 to the power k plus 1? So we can say that 2 to the power k plus 1 is less than equal to 4n. Hence we know that whatever is our value of n, this size of trie is always going to be less than equal to 2 to the power 4n. 4 into the array size, and array size is 10 to the power 5. So if we bluntly form this segment tree in the form of a complete binary tree, taking into consideration extra elements, the maximum size that we can reach or we shall be reaching is 4 into 10 to the power 5, which is not a big deal. Make sense? Less than equal to 4 into 10 to the power 5 as per the question we have started with. Drop a quick yes or no if it is clear or not, and then we'll be proceeding into the time complexity analysis. Is it clear? So array size n. What I've shown is this is the trie size. Size of trie is less than equal to 4n. Great. Maybe I'd like to hear from everyone, whoever are present. And if you have any doubts, please feel free to ask. Okay, so now let's proceed to the interesting part. What is the time complexity? Now we will go totally theoretically. So let us see if we have to update something. Update operation. Can you see it's pretty straightforward? What is going to be like whatever is like suppose this is the node, this is the node that I want to change. So I just have to go along its ancestors. Explain this again. Second point, second condition. Second condition is means when the array size may not be a power of 2, what I'm doing is I'm finding out that what is the nearest power of 2. So I'll be adding that many zeros, I'll be padding that many zeros, and thus I'll be allocating more elements. So the size of trie is going to be slightly greater than 2n. It won't be exactly 2n. Now I'm finding an upper bound for it. That what is the size of the trie? I know that 2 to the power k array elements means 2 to the power k plus 1 total number of nodes in the trie is going to be there. And hence I am then forming this upper bound. How? Because I know that n is greater than 2 to the power k minus 1. Because I know that k is the smallest power of 2 which is greater than equal to n, that is why I can easily tell this. And when I use this over here, I am basically getting this expression. 2 to the power k plus 1 is less than equal to 4n. And hence size of trie is less than equal to 4n, and this is according to the value that I had started with, that n consider it to be 10 to the power 5. Make sense? Any other line that you're confused with? Okay, I'll come back. If there is any other confusion, you can write down. So what is the update operation? Basically, if we are changing this leaf node, we have to change all its ancestors. How can we reach the ancestors? Or how can we reach this particular node? Suppose we have only the root. How can we reach this node? We can say that from this root node, whatever two children we have, we know their ranges. So if I know that my target element lies in my first half, I can go only to my first half. I won't go to the other half. In this manner, I can first go over it. Then I can see that, okay, now this target index lies in my towards my right, in my right index. So it will basically go to its right index. And that's basically right child. And this is how it is going to proceed, and we are going to get all the nodes. We'll update over here, and then when we'll move up, we'll say that what you have got to do is, you have two children, whatever their current values are, add them and place it to yourself. It will say that, okay, whatever its current value is y, and its current value is z, I will assume y plus z. It will tell its parent will also do the same thing. Whatever its children are, it will keep the sum. So how many nodes are changing? 1, 2, 3, 4, 5 in this case, and in general case, can we say that this is going to be exactly equal to the depth of the tree? No less, no more. This is exactly equal to the depth of the segment tree. Yeah, so it is going to be order log n. I am not writing log of n to the base 2. The log of n to the base 2 is actually the operation, but this is a kind of approximation. Even k, we know like k is related to log of n, and this is actually order k or order k plus 1, whatever you say. So makes sense. Now the interesting part. What do you think about the range query? Will it be a good complexity always, or will it depend on what we are querying? Something like this you will have, then something like this. For this, let us analyze that how we'll be performing the range query. Whenever I say that I want from here to here, okay, somewhere from here to here, there may be even more children I want in this range. So what will I say? That, okay, you are not completely involved. This node is not like, this node represents the entire tree. So entire array is not completely involved in this range that I'm targeting. So it has to request its children that send me all your values, whatever you find intersecting with your requirement. It will be between order 1 to order log n. Let us see, Hitesh, let's dissect it more strongly to get a more accurate analysis. What is the total number of nodes that I may have to visit? Can you see that these nodes are quite many in number? These can be quite many actually, like suppose there are many levels which we have not mentioned over here. So maybe they are like quite greater, you may have to read them. Or there is also another thing which you might notice. When we are coming down from here, we know that both nodes are important to me. Why? Because some of these nodes that I'm targeting lie in my left subtree and some of the nodes lie in my right subtree, right? So I can't ignore any of the child over here. I'm sorry, I won't use yellow. So this subtree is also important to me because these nodes are important to me, and similarly this subtree is also important to me because these nodes are important to me. And this node only contains the sum of all the nodes from like in the last level. So this contains only the sum, so this one cannot help. I have to see in detail. So what can we use over here? We basically we know that from here also I may have to visit both the nodes. From here also I may have to visit both the nodes as I visited over here. I may have to visit. I don't know if I do have to visit, but I can't guarantee at least now how many I have to visit. The thing is that if we have to give a firm upper bound to the number of operations in our time complexity analysis, we have to be very sure about how many nodes we are visiting, formally and theoretically. Okay, so let us analyze this. From here, I have come to these two nodes. Will it ever happen that I'll have to visit this node, this node, this node, this node, and from all the four I have to go downwards? Yes or no? The question is that for finding this range, I had to come to all these nodes. Now forget this range. This range can be anything. Will it ever happen that from here, I may have to come down over here, over here, over here, over here, over here, over here, over here. Basically, I have to reach the children. Will that ever happen? Forget this range. The range can be anything. So will it ever happen that all of these will need to depend on their children? Okay, 50-50 till now. Let us get some more answers. Like today you should be shooting questions. Anyway, worst case we need two nodes which are not grouped. Interesting. Okay. So what convention are we using? Let us first write down. Node has these conventions. The value of at most 3 nodes will be taken. Another interesting point. So these are the characters of the nodes with respect to a particular query. The first character is that no intersection. If I've reached a node and there is no intersection, I can say that okay, I cannot contribute anything. There is no part which is common. I represent L to R and you are asking from me some L dash to R dash. Absolutely no difference, no intersection. There is no intersection between that. So I can say that okay, like just return it. It will not visit its children. Don't visit children, right? We want to see key how many nodes will ask their children to send them values. We are going to check that. Just a second. Okay, don't visit children. Next thing, what can we say? That if it is fully covered, if L and R is my node, so this is basically my node and this is the target range, this is the query. So if I say the query fully covers the node, L dash is less than equal to L, less than equal to R, less than equal to R dash, then it will not visit the children. It will say that okay, take my value, you are done. So again, don't visit children. Don't visit children. This means that this range is fully covered in the target query. Fully covered. Next thing what we want to see is that which is the case when partially it is covered. Partially covered means these are the cases. This is the only case left. It is uncovered, this is fully covered, and now it is partially covered. Partially covered means we can say that this is our node and it takes the first half. It takes the first half, beginning part. What can we say then? We need to visit both the children. Why? Because maybe one child will tell us about the left part, another child will tell us about the right part. Right part maybe kuch part common hai. Right part also contains some elements which are there in common. So I need to depend on its children. The left child will tell me about this part, the right child will tell me precisely about this part. इसमें मुझे कितना मिलेगा? So basically what I want to say is कि ये जो covering है, जो L dash R dash के साथ जो intersection है, that is towards the left. The B part is towards the right. जो कुछ ऐसे होगा, इधर कहीं पे होगा. This is right. And the third part is अगर बीच में हुआ तो. अगर ऐसा है कि हमने बीच में कुछ part मांगा तो, something like this. We are requesting some part in between. This will say that okay, in middle we have that intersected part. Now we will analyze what are the cases. अगर ये middle वाला हुआ, if this is the case कि at any level we have a node with which LR actually falls in between. LR falls in between. What is the important thing we can infer from here? If this is a node, these are certain nodes in that level. I am observing only one level. I know that this is covered, like only a part in between is covered. Can we say that because we are targeting a contiguous range L dash to R dash, it must happen that L dash starts over here and ends over here? Can we say? Because R dash, if R dash would have extended beyond this, definitely these elements should have been covered, right? But because these elements are not being covered, that means R dash is strictly this particular value. And L dash is also, according to the similar argument, it is exactly this value. This is the first observation that we are using, that if a node is being covered according to this particular category, then there is only one node which will lead to its children in the next run. This is the only node that will call its children. So how many nodes of the next level will be called? Only 2. It will call only 2 children. Only 2 children. What case have I considered? That one of the nodes is going to be covered according to the C type covering. So this is C type covering. Got it? Next, I'm not looking at what are fully covered currently, but in this case we know if it is C type covered, means covered from between, we know that other nodes cannot be covered. Does this make total sense? That this node cannot be covered. Why? Because if this node would have lied in the range, or any part of this node would have lied in the range, then this would have also lay. This part would have also been covered. I cannot choose some L dash R dash which would have taken this part and then some part of this. Make sense? Quick yes, no please. Great. So now running and rushing to the next part, which is B type or maybe A type. A type says that the left part will be covered. So when we have these kind of nodes in a certain level, how many nodes can be covered in the left? Suppose this node is covered in the left. What can we say? Can any other node be covered in the left? No. We know that no part to the right can actually contribute to our range. We know that all the parts which are there in our left, from the right they will start getting covered. So maybe we will get this covered completely, and maybe this one will get covered, some part from the right. Can you see? That according to basic idea that we are using, one node can be uncovered, can be partially covered with the remaining part to the left, and over here the remaining part is towards the right. This kind of complementing. What we basically am identifying from here is that if this particular category is there, then there can be only one node which will lead to the children. Over here there can be at most two nodes which can lead to the children. The other nodes, if there are any in between, they will not lead to the children. Is this point totally clear? They will not ask their children why, because they are fully covered. It cannot happen that they are also partially covered. Only the extremities of a range can be partially covered. The other nodes in between must be fully covered. Make sense? If you are covering somewhere from here to here, then we have the A type over here, we have the B type over here. We may have this also fully covered, but whatever are there in between, they must be fully covered. They may be uncovered also. Maybe if their parent has already considered them, then maybe their parent will not call them only. In that case, they'll be uncovered. But we know that, okay, they will not call their children. Who will call the children? Only this partially covered nodes. They will only call the children. They will not visit the children. I hope you have understood why. But these partially covered nodes will visit the children because they don't have the sufficient information to answer for L dash R dash. They have to ask specifically for that L dash R dash. So they will visit the children. And this tells us that because we have at most two partially covered nodes in a range, we can uh, basically call at most how many children? Two from here and two from here, so four children. We can cover four children from here. We won't be calling more than four children. So what can we say? That number of partially covered nodes in a level is less than equal to 2. Hence, number of nodes from the next level involved is 2 plus 2 or 2 into 2, that is going to be less than equal to 4. This is the total number of nodes. I don't know whether they are covered, uncovered, partially covered. I totally am unaware of that. But I know it will definitely not cross this. And I know partially covered nodes will not be crossing 2. So, what this tells us is that from every level, only 4 nodes are important to me. And we know out of 4 nodes, maximum 2 can be partially covered, which can lead to their children. Rest all have to be totally covered or uncovered or whatever. Okay? So what this tells us is how many nodes am I visiting? If I know that every level from its parent or from its previous level, in every level 4 nodes are being invoked, that means number of levels is log of n to the base 2, or we can say 4 times log of maybe just a second. Yeah, I'm sorry about that. So maybe 4n you can mention that, but for the time being I'm just writing it as log n, or you can keep it as log capital N. N is the number of values in the trie multiplied by 4. This is the total number of nodes that are going to be visited, and that's it. These nodes, even if they're uncovered, just a second. Hello. Uh-huh. अच्छा अच्छा एक सेकंड धरी दीजिए एक सेकंड. Just wait for a second. If you have any doubts, please do ask in the chat. I'll be answering. I'll come back in half a minute. Just a second. Yeah, I'm sorry about it, and just a second. After 5 minutes, I'll be receiving all the messages because there is some delivery going on. Okay, I'm sorry. Yeah, there is some delivery thing over here. So after 5 minutes, I'll be taking all the queries. So whatever you have in mind, just write down. After 5-10 minutes, I'll be receiving the queries. I don't have the device with me currently. So anyway, this is the number of operations. There's a number of nodes that we are visiting at every level, or all levels combined. This is that value. So I hope it is clear. And from here we can say that this is the total number of nodes involved in our range query operations. So our range sum is going to consume order log of n time complexity. Make sense? If you have any doubts, you can just keep that posted. And I'll come back to it if you have any doubts. But maybe we can move on. What is the time taken? Now we'll discuss the implementation just after this. Before this, let us first analyze what is the time taken to form the first structure of segment tree. We know our segment tree is going to consist of how many nodes? It is going to consist of maximum 4n nodes, less than equal to 4n. What is the time complexity of forming it? We can directly say, we can use a DFS kind of an approach. We can say that currently you are only beset with this range 0 to n minus 1. So move downwards, cover all the values over here, and then travel upwards. And then what we get is that we'll keep on combining these values, and finally we'll receive the sum over here. So what we are doing basically is, at these terminal ends, what we are saying is a of whatever, or maybe your segment tree of whatever this index is, whatever the index of this part is, we actually represent it by a range. TL TR is actually the range that it belongs, that it identifies. So we know at the terminal, at the leaf part, TL and TR are the same thing. It is either 1 1 or 2 2 or 3 3, something like that. I hope the audio is on. Okay. So what we can say is tree of 2 is equal to 2 basically is what is the number of this node. Now how we mark it, I think that is also important. So let us cover that. This is a very easy way in which we can travel from one node to the other. We know that there is a binary tree approach, dot left and dot right, but even while teaching tries, I emphasized on the same thing, that sometimes using arrays is far more easier and intuitive. So we will try to index it and we can try to see how that works. So these are the indices that we can use: 1, 2, 3, 4, 5, 6, 7. What I'm doing is that just at every level, left to right, I'm just marking the indices: 8, 9, 10, 11, 12, 13, 14, 15, right? Now what we can say is, there is a very interesting observation. For any node, you see the two children have a special relation with the number of the previous node. For 5, or for any node which is marked as x, we basically have 2x as the left child and 2x plus 1 as the right child. Just a second. Yeah. So point update, left child equals to great. Yeah. Point update at every index. Yeah. Okay. Point update. Okay, Hitesh, that's very interesting. I'm happy that you pointed out this. Point update at every index, if we do, what is the time complexity? We require n log n, right? Because how many elements are there? Order n. And how many, what is the complexity for one update operation? Log n. So n times log n is required. But this build operation is actually a bit more optimized. I'm not telling that we always require it, but this is far more advantageous. So where are we? Okay. So for any node which is marked as x, what we can observe from here is the left node is 2x and the right node is 2x plus 1. Okay. Does this make sense? I know this is a slightly advanced level course and it's not easy for all, But I'm trying to give as much details as possible. If you think rather I should be going slow, then I can probably do that. So I hope it is clear to all of you. Because these are such topics where you will actually have 10, 15, 20 lines of code, and at some moment of time you can feel that okay, now I don't know how to go ahead, I don't know how to play with this structure. So when you understand these things, you will be very comfortable in dealing with these structures. So if you have any doubts, feel free to ask. Makes sense, right? So what can we do using a simple DFS? We can say that first solve for the children, then we can say something like this: tree of x equals to tree of 2x plus tree of 2x plus 1. Make sense? There are again notifications. Okay. Okay. So this is basically how you can calculate for these nodes. Okay. And for this node, which is the terminal part, you can basically write that it is equal to a of I, whichever I is involved. We'll look at the exact code. You can understand that here you can directly place the array elements, and for these parts you just have to use this formula, that's it. And because you know you never have that case that the right child is not there. क्यों? क्योंकि हमने वो padding कर लिया है. We have already done the padding. So you don't have the case that for a certain node you have the left child, you don't have the right child. You don't have that case. Yeah, happy Engineers Day to all of you. Ah. So coming back. Where were we? So what is the time complexity of this operation? This is called the build operation, where we are first building the tree. And we are doing this in a slightly different manner compared to the point update, n different point updates. This should be small n and that is capital N, but that doesn't make any difference because small n is equal to order capital N. So build operation, what is the time complexity of build operation? Any idea? We know space complexity of this structure is order n. I hope you recall that. So what is the time complexity of this structure? We are slightly running short of time. Like we have taken more time, but anyway, we'll catch up. After this, we'll solve problems. We'll come out of these theories, but let's end with this. N log n. What about the rest? Log n. No, we are storing all the values. If you have correctly heard, we are basically storing all the values in this structure. In try, we are going to each of the nodes and we are first initializing those values. So there are n nodes, so definitely n to hoga hi. N will be the lower bound, I think. There are 4n nodes, so 4n has to be there. We are basically going to go to every node and construct these nodes, construct their children, then find their values, which is the sum of the children, and basically we are going to do this for all of them. Got it? So what is the time complexity of that entire thing? It cannot be less than n, it can be log n. Think a bit more. So having come through such kind of theory, I would expect some correct answer from some of you. Think of DFS. When you do DFS, what do you do? What kind of a data structure is this? What kind of a graph is this? let's like accept. Let's come to the ground that it is a graph. So what kind of a graph is this, and what is the time complexity of doing DFS? Why DFS? We are doing DFS from the root, right? From the root, we are telling that find out the children, come back, and it's like finding the sum of nodes within a subtree. So within every with every node taken as a root, you need to find what is the number of nodes within that. So it's a straightforward question. What is the time complexity of build operation? I'll wait till 6:46 and it would be nice to get some correct answers. Think about it. Maybe you can look at uh, my implementation of range sum segment tree. This is what I'm doing. So TL and TR are basically denoting my ranges. 4n. The rest, tell me only in asymptotic time complexity, because everything is an operation. You're calling something, that is also an operation. You are combining two values, adding two values, that is also an operation. So forget about those things. Just tell me in asymptotic time complexity analysis, order of what. So anyway, what are we doing in build operation? We are saying that if it is a terminal node, that means the left index is equal to the right index. Okay, n log n. Okay. So okay, let us now break the ice over here. See, a simple DFS means what is basically a simple DFS. Time complexity of DFS is always order n plus m. Agree or not? This is the time complexity of DFS, order n plus m. What is m? Number of edges. What is number of edges in a tree? It is equal to n minus 1. So what can we say? That by the very definition and by the very knowledge of DFS, we can say it is order n. Why it is order n? Because every node we are visiting exactly once. And over there we are doing order 1 operation. In every node we are doing order 1 operation. We are visiting exactly once, we are doing order 1 operation, we are returning. From here we are calling the other nodes, but that is a different thing. For every node it is order 1 operation. How many nodes are there? N nodes or order n nodes. So we can say order n is the total time complexity. Can we say something like this? Is it convincing? Let us look at what I have done over here. I have simply called the children the way you do in trees, your binary tree questions. One of you was asking that how difficult it is compared to like binary trees. So in binary tree, there is a simple operation, and then you are doing just one operation, which is merging the two values. You are saying, I know the value for my left child, I know the value for my right child, so just merge them. How are we doing that? We are basically adding these two values. We are saying that add those two values and return to us. This is how we are doing it. Straightforward. We are going to store it over here. So what are we saying? We are basically saying that okay, we'll call them using some computation of TM. I'll come to that later. But can you see that the time complexity analysis per node, this is going to be definitely order 1 because this merge operation is order 1. All these operations are also order 1. So for every node it is order 1, and hence we can say that summing up over all the nodes, the build operation is order n. Does it make sense? So conceptually, yeah, Ivan, your final answer was right, but it would be nice to hear a yes, no from all of you. Let us see. Let us then see. Let us then print this x, and let us see how many times we are printing it. Okay, I see quite many yeses, but okay. Let us see how many times we are printing x. That will actually show it. So we are going to build it and no queries. We are going to add 8 numbers and we are going to print this. Okay, or we are going to just enter 4 numbers and we are going to print this. So Java C range sum. Okay, CD. I don't know where I have it. Competitive programming segment. Competitive programming segment. Segment trees. Okay, I should be able to find your Java C range sum Java. Okay, I think that thing is now required. I didn't do it. Java range. Every day I forget doing that. Okay, so I want to enter 4 numbers. So there you go, 2, 4, 3, 1, and then nothing else. So can you see that every node I am visiting exactly once from 1 to 7. Why 1 to 7? Now come back over here and see 1, 2, 3, 4, 5, 6, 7. Can you see that for these 4 terminal nodes, how many total nodes are there? 1 to 7, and I'm visiting all the nodes exactly once, 1 to 7 in this build operation. So this is and you can see I'm visiting exactly once, and then either I'm going somewhere else, or somewhere else means in the build operation only I'm going to some other x, or I'm doing some merge operation basically, which is order 1. So from here I can say that this is exactly order n. Great. So now let us look through rest of the codes, and if you have any doubts with regard to build or any other part, please do ask. I'll explain every line. If I skip a line, do write the line number. I've zoomed it so that you can understand it more clearly. I'll explain it line by line. Do ask if you have any doubts. What I've said is, first of all, this is my segment tree, an int array, as simple as that. And this is my array, static int a, which you may not require anywhere. So, okay, either you need to pass it in the arguments, or basically you can keep it outside. So let us see, when I've taken that this is my input array size n, I'm making these initializations. So now my tree variable is going to have 4n elements, and my a, which is the actual array, that is going to have n elements. So far so good. I'm taking the input and then I'm building this. When I'm building this, what are the things I'm passing? I'm telling that your root, the root index is going to be 1. So we are referring to this root as 1. Okay, this 1. And we will say root has to take care of this range, 0 to n minus 1. 0 to n minus 1, this range is going to be taken care of by the root. Let us see what build does. Build will say that, okay, if my left index and right index are same, that means I am a leaf. If I am a leaf, then I don't have to go to any children. I have to. Can you explain how the recursive build function works visually? Exactly, I'll do that. So we are doing something like this. Let me first explain through this code and then I'll be showing it. Thank you for pitching it up. So for the leaf, what I'm saying is that if the TL and TR are the same, then just initialize it. Tree of x equals to a of TL. TL, we know that TL is equal to TR. So it is like you have reached a leaf where it is something like 5, 5. So you say, okay, go to index 5 of the array. Whatever value is there, place that at this index of the tree. This is my segment tree. And then return it. If it is not the case, if it is like not equal, that means it is not the leaf. So we will say now we need to depend on our 2 children. So now we have to construct the 2 children. How can we do that? Something like this. We can say TM is the half, basically TL plus TR by 2. I have written this in a fancy manner. TL plus TR minus TL by 2 is the same thing. Just for overflow reason, this is how it is written. So when we calculate it and when we go for it, we say that the left node has to take the charge from the left index to the middle index, and the right child will take the charge from the middle plus 1th index to the rightmost index. Make sense? And then we will merge it. We'll say that, okay, take the 2 values which you have already stored in 2x and 2x plus 1, take those 2 values and merge it, and then you will get 3x. So let us see how this works. Let me try something. Oh no, it can't. Anyway, so what am I doing is I am calling build of 103. N is 4, and what were the values? The values were 2431. Okay, so let's format. Did I click anything? Okay, 2431. So this is stored in A. Okay, I'm sending this 103. This is 0, 1, 2, 3. Now what we can say is where was I? Okay, now we are calling the root. So there we have the root. The root has x equal to 1. It will say that over here my TL value is equal to 0, my TR value is equal to 3. Okay, we are having in this manner TL comma TR. I'll write in that bracketed manner. Since they are different, I'll first call my children. I'll call build on my children. What is going to be TM? TM is going to be 1. TL plus TR by 2, something like that. So TM is going to be 1. So middle is equal to 1. So when I'll call my two children, one will be on the index of 0 to 1. The other shall stay with the indices 2 to 3. Make sense? We'll ask him that, okay, your x value is equal to 2x, which is x equals to 2. And for this, it will be 2x plus 1, which is x equals to 3. X equals to 3. So far, so good. Now, from each of them, we'll be calling the children. As simple as that. We'll be calling the children. Why? Because again, TL and TR values are different. So we'll again call the children. We'll say that, okay, your TL, TR value are equal to 0. Why? Because TM is equal to 0. TM plus 1 to TR, it comes out to be 1, 1. So we can say, okay, for you, and you are getting the x value equal to 4, and here the x value is equal to 5. Why? 2x plus 2x and 2x plus 1. Similarly, here we get, do write down in the chat if it is clear, if the visual is clear. Over here we are getting TM value equals to 2. So we have 2, 2 over here, and we have 3, 3 over here. We have x value equal to 4, sorry, x value equal to 6 and x value equal to 7. And now what can we say? Since these two values are matching, since TL and TR are matching, we are in this base case. If TL equals to TR, what will we say? 3x is equal to ATL. 3x equals to ATL. What is TL? TL means we'll go to this particular index, we'll get the value 2. Thanks, Hitesh. Shall be nice to hear from the rest of you. Here also we have TL equals to TR. What is TL? This is 1. So we will go to this index and we will fetch this value. We'll have 4 over here. Similarly, over here we'll do it, but in terms of how DFS works, first we have to complete for this node. So how will this take its value? This will call its children in these lines. In these lines it will call its children, build operation. Then it will take its own operation. How? It will basically add them. Merge means I'm calling this function where I'm adding the two values. So I'll go and add the two values, saying that, okay, tree 4 plus tree 5 will give me 6. Similarly, we can go over here and we will get, sorry, we'll have to go to the 2th index to fetch this 3 and we'll get there 1. Over here, when we'll come again, we'll be merging it, so we get 4. When we'll reach over here, we'll be merging it because this is not in the base case, so 6 plus 4 is 10. Make sense? Now let us then run it and see if our hypothesis was correct. System.out.println x 3x. I'll run this. I'm sorry. 4 2 4 3 1 2 4 3 1. 2 3 1. Got it. So only for the internal nodes we are printing it here. Okay, good to know. So only for the internal nodes I'm printing it. I'm not printing it for the leaf nodes, else I would have to print it over here basically. So for the internal nodes, 2 6 3 4 1 10. Let us find it. 2 6 3 4 1 10. Got it? So it is matching to our visual. So that's it, and we also see that it is getting printed exactly once, which means the complexity part is also fine. So now currently, whenever we refer to a node, we have to fetch through its index. That index is going to tell us its value. If the index is x, we know tree of x is the value. Okay. So for the rest of the operations, it will simply be array fetching. We have to reach the correct index and we have to find out. How will we reach the correct index? We have to start from the root, because we know that the root is of index 1. For all the other things, we can reach in log n time. Any node, if you have to find out that, okay, for TL or TL equal to TR equal to this kind of a value, you have to go along that route and find out. You can find out that, okay, if TM is greater than or equal to your target index, you have to go to the left child. If TM is less than the target index, then you have to go to the right child. This is the basic intuition that we'll be following. Let us check it through our code. We'll be updating it. So this is something that I have found. Every query I have taken something like this. First we have update operation. So at B I'll be placing C. At bth index I'll be placing C. So again I'm telling the same thing, that call the first index of the tree. Yeah, first index of the segment tree, which actually refers to this range. So I am not forcing the segment tree to remember its range. I'm telling that, okay, great, and will this build function also work for n not a power of 2? Definitely, like you can. I may have not compiled it. Actually, let's not compile it. Then I can probably show you. 5. Suppose 5 elements, 1, 6, 5, 2, 3. These are my internal nodes. Maybe what I can show is, let's print this also, and let's also print x. Let's also print, or maybe x I can print over here. X and 3x. Okay. So now let's see what happens. 1, 6, 5, 3, 4. Okay. So this is what we get. 1, 2, 3, 4, 5. Where is 5? We should not see in this manner. Basically 5 means we are approximating it to 8. There are 8 elements, and if there are 8 elements, then our number of nodes that we require is somewhere around. This is a bit weird. Okay, we are getting 9. We are not getting more than 9. But had there been 8 elements, we would have got something like 15, right? Let's maybe try it on it. 1, 6, 5, 4, 3. So this is going to have, okay, got it. So what I'm doing over here is something like this. This represents from 0 to 4, and hence what happens? This will call this node on 0 to 3, and it will call this node on what? It will call this node on 5, 5. So I'm actually settling it over here only. I'm not extending it over here. I'm just finishing it over here. I'm saying that over here, whatever was our last element, 4. So we are having this 4 over here. So you can see this index is 1, this index is 2, 3. This index, amazingly, we are not taking anything over here. These indices are 5 and 6. These indices are 7 and not 5 and 6, I'm sorry. 4 and 5. These indices are 8 and 9. That's it. We don't have the other so far as I am observing it. 1, 2, 3, 4, 5. 0, 3 means it is 0, 1, and it is 2, 3. So ideally we should be having these two as well, 10 and 11. Are we not having it? Okay, so let's figure it out now. 0, 0, 1, 1, 2, 2, 3, 3. Now, okay, what did I mention over here? What did I mention over here? Update operation n-1, n-1. Okay, got it. So while conceptually I'm trying to do this, what eventually I'm doing is I'm dividing into two ranges. I'm doing something like this: 0 to 2 and 3 to 5, 3 to 4, which is also fine. So what I'm doing over here is there should be 5 leaves, and there is 5 leaves. I'll tell you what I'm doing, and this is just that it works, but thank you for pitching the question. I never thought about it, but this works pretty well. So you can see from 0 to 4 we are having elements. What this does is this has 0 to 2 over here, this has 3 to 4 over here. What this does is this has 0 to 1 over here, and this has 2 to 2 over here, and now you have this saturated over here. This one will find out two different nodes, so it will have 3 3 and 4 4, right? And then what can you see over here? You can see basically something like this, 0 0 and 1 1. So both the constructions are correct. Even this construction is correct that I showed you. If you have to implement it, you can actually find out at every index Tm is a power of 2, has to be a power of 2 or power of 2 minus 1, something like that. But it is better, or like this approach also works. It has worked everywhere, I think. Anyway, it has been some time since I've last taught segment trees, but I never actually observed this. This is the first time I'm observing. So what do we have over here? We are saturating, we are not extending it beyond this. So that is why over here only it gets manipulated at the base case. This is 1, this is 2, this is 3, this is 4, 5, 6, 7, 8, 9. And this is the reason you are actually getting 1 to 9 over here. You're actually getting values, x values from 1 to 9 over here. You have 9 value, which is the highest value over here, right? And if you tally the values 16534, it will exactly be as expected. 16534 means something like this, 16534. So we can calculate it. This is 7. 7 plus 5 is 12. 3 plus 4 is 7. This is 19. So we can have it something like this. 19, 12, 7, 7, 5, 3. 19, 1, 19, 12, 7, 7, 5, 3. You have the first 6 values same, and now for 7, 8, 9 we can check. For 7 it is 4, for 8 it is 1, for 9 it is 6. 4, 1, 6. So let's check. 4, 1, 6. So the values are matching. Shouldn't x equal to 2 have range 0 to? X equals to 2 have range 0 to, right? Over here, I think you were commenting about this particular diagram. So yeah, according to the code that I have written, yes. So anyway, the idea remains the same, and the complexity also, everything remains the same. The upper bound and everything remains the same. And I hope hence the update operation is clear. For the leaves, we are basically doing it in one go. Okay, update operation I did not explain. For the build operation, the leaves I am updating in one go, and for the non-leaf nodes, I'm calling these. But to answer your question whether it works or not, I think you're convinced that it works always. I hope you can always, like, now you're confident that it will always work, right? You can keep thinking on it, and if you have any counter example or anything in mind, any counter argument kind of a thing, you can post it. We can debate on that. Let us proceed now. This is the update operation, where what I'm telling is that from TL to TR, this is the domain of this X. Again, I'm mandating it. We don't have to remember anything. Power of 2, not power of 2. Forget about those things. The main function is going to say for the root, this is the range. The tree nodes know that how they have to divide it among the children. There is a particular formula which is using this TM. It will never go differently. It is the same formula. And this formula is actually the same as I had written over here. So, okay. So what are we going to say? Something like this. That call both the children. In update operation, just to make the code easier, just to make the coding implementation easier, I am updating on both the children. And what we are seeing over here is, if we know that we are visiting two children, we are asking that, okay, in the pause position, POS, we have to place value. We have to place this value. All the other positions remain the same. Pause and whatever its ancestors are in the tree, we have to change that. And pause is with respect to A, not with respect to your tree, not tree index. Pause is an array index. Remember this, okay? Pause is an array index. Clear? Next, what we can do is, what I am doing is, if I reach the correct leaf, then okay, I'll say that okay, I am substituting it, go back. When my parent will get it, my parent will simply say that add my two children. update my two children, whichever will get updated, well and good, and then I'll just add my like update my own value by adding the new values of my children. Easy operation, intuitive operation. Now the question is about extra computation. Are we computing extra things? Let us see. We are calling two children from every node, but whenever we are visiting a wrong node, we are telling that if TL is greater than pos or TR is less than pos, then return. When TL is less than greater than pos or when TR is less than pos, then we'll be returning. What does this mean? When are we going to allow it? When is this going to reach these levels? Only when pos this particular position lies in TL to TR. Makes sense? So what I'm saying is if TL TL is greater than pos and TR is less than pos, then return it. Means you have come to the wrong node. We don't require you. So when are we going to reach the children? Again, the same kind of analysis as we did in range queries. We are saying that when are we going to proceed to the children? From which node? We are going to proceed only if this condition is not satisfied. When is this condition not satisfied? When is this condition not satisfied? When basically TL is less than equal to pos and pos is less than equal to TR, right? Just the complement of this. This is OR. So if either is satisfied, we will say return. So does the complement of this means that we have to visit the children? What does this mean? That it is actually a valid ancestor. If we are changing a node and if we know that a particular node has this particular range within which this node lies, that means this is definitely the ancestor. Makes sense according to the observations we made initially, that this node which encloses this position is definitely an ancestor. So this node definitely has to get changed. So which nodes are we using? Like basically which nodes are we not returning from directly? They are the important nodes, whichever nodes are important to us. And from those nodes only we'll be calling both the children, and we'll find out which child is important to us. Whichever child is not important to us, we will say return. Make sense? So this makes our implementation quite easier. Else we would have to do something like this. If TM is something that will also work. Had we written that if TM is greater than equal to pos, then do this, else do that, that would have also worked. But it is not required. We can just call both of them, and whichever is wrong, we will definitely see that either this is previous, like this occurs before our position, or this occurs after our position. So either way we can ignore it. And if it is the exact index, then very good, just return it. And if it is not the case, it is not the leaf, it is also not an invalid one, this is an ancestor, and hence what we'll do is we'll call the two nodes, two children, and we are going to merge it. Make sense? This is actually one of the easiest implementations of segment trees, and believe me, there are a lot many ways in which it is implemented. So in this way you can actually write any update function. Why have I written this merge separately? Because in merge function I've actually written that okay, you need to add this. Suppose it was finding the max or finding some other operation. I would just have to change this merge. I can just change this merge and I'm done. Maybe I have to change this part also, what I'm updating. Or maybe when I'm querying it, I may have to change that base case. But this particular case remains the same. Make sense? Any questions? Any questions in update or build? Any doubts? Any counter thoughts? Else we'll move to query. So does anybody have an issue if I extend the class by around 15 minutes? Do you have any issue if I extend the class by around 15 minutes? So like before we continue, tell me these two things. Whatever I have told till now, this update operation, If you need a visual, there it is for you. You want to do an update, you have sent to it that okay, this is my position. This position somewhere lies over here. There, and actually the TL values are something like this, pause and pause. From this X, you have to reach over there. So we can go like this, like this, like this, and then we are reaching it. At every step, what are we doing? We are calling both the nodes. And then we are saying from here, we don't have to go further. Then from here, I'm calling both the nodes. I'm telling from here, I don't have to go further. Then from here, I'm calling both the nodes. I don't have to go further. From here again, I'm calling both the nodes. I know from here, I don't have to go further. So what is this unnecessary node? What is the number of unnecessary nodes that we are visiting? Number of levels, that means unnecessary nodes we are visiting. So that is not a big problem. We can say twice the number of levels is the number of nodes that we are visiting. So that is not a big problem. 2 into okay nice. So 2 into log n is basically the number of nodes that we'll be visiting. Great. So where are we? Is it convincing? Is the visual convincing that our update operation, despite visiting extra nodes, is still order log n? I think with fast responses we can move faster. Okay, great. So let me quickly brush up this part, query part, this code. If you have any doubt with regard to any line number, you can ask. Okay. Anyway, okay. So what are we doing? We are basically now querying that from L to R, tell me what is the sum. That is what I am asking from the main function. Tell me the sum from L to R. What this will do is initially the root is visited and the root has a TL value equals to 0, TR value equals to n minus 1. Then what we are saying is that if there is no intersection, when is there no intersection? When our target query finishes before the query, our target range finishes before this node range, something like this. So no intersection case is interesting over here. Suppose this is my LR, this is my node. So if my query range is somewhere over here, that is it finishes before LR or if it starts after R. These are the two cases when my query has no intersection and I can simply return. There is nothing I can gain. So what is this case? This case I can say this is just R dash less than L. And what is this case? This case is L dash greater than R. I hope this is clear. So what I'm doing is that I'm just telling that if either is the case, then return it. So R dash less than L and over here greater than R. This is what I'm doing. R dash basically is TR, L dash is TL. Make sense? I'm saying that return 0. Why return 0? Because I want to find the sum over a range. So if a particular node does not contribute anything, he says that okay, take 0 from my place. Don't bother me much. I don't want to call my children and bother them. Take 0 from me and end the matter over here. I'm sorry. What do we know? That total number of nodes visited at a particular level is 4. So for all the 4 nodes, either of these operations will take place. Either it is uncovered or it is fully covered. What is the fully covered case? When we know that L dash and R dash lies within L and R. And this is that particular case. We will say that we will return tree X. And what is the other case? When it is partially covered. We'll not do if else anymore. We'll just say that okay, call the two things. The next node, which is the left one has basically the index 2x. We are going to say you have to give me the values, the sum of the values from TL to TM. Again, same way of having it. No difference. And we will say to the right child that fetch the sum from TM plus 1th node to TRth node, or basically this element to that element, and fetch me the sum. If any part of it is basically your, what is that called? If any part of it is outside the range, then you will get 0 from there. Over here I'm not checking whether the left half is important to us or the right half is important to us. I'm just saying call them and just add them and return the result. Why? Because if any part is totally uncovered, it will return 0 from here. If it is totally covered, it will return full value. If it is partially covered, it will do these operations. And theoretically, we have seen how the entire thing will yield us the value within order log n time. So, is it convincing that whatever theory we have discussed, this is a successful translation to the implementation? Have we successfully translated it into the implementation? Does it make sense that whatever we discussed theoretically, which turned out to be order log n, is exactly the same that we can observe currently? It is order log n. I'm sorry. Yes or no, folks? Code is simple enough. Okay, great. Nice to know. So that's what I'm doing. You can see this is how easy segment tree is. You code the functions and then you're done. You can do all these complex operations. Let us take any example. Let me cover these up. We don't require these unnecessary println statements. I'll just take an example and we will just convince ourselves that everything is working fine. So suppose you have 5 elements, 2, 7, 5, 1, 3. You have 5 queries. So first time I'm going to ask you what is the sum from index 1 to index 3. The answer should be 7 plus 5 plus 1, which is 13. Okay, I'm sorry. It should actually start from 213. That is how the query looks like. B C sum, right? I'm sorry. A B C. A is basically the type. So 213 we get 13. Then suppose let's say we change one particular index. We want to change the third one and make it 10. So 1 will get changed to 10. Now if I query the last 3 elements, how should I query this? Index 2 to index 4. So 2 to 4. 18. 5 plus 10 plus 3. 18. Make sense? Now if I query about this initial range 213, it's 22. So it remains as 213 means basically these 3 elements. So 12 plus 10, 22. Now suppose maybe I can decrease this. 5 I'll be decreasing to maybe 1, or we can even keep it negative. Let's for the moment keep it which index it is. Okay, 1 1 or 1 2 1 1 2 1. Okay, this was actually the last operation, that is why we could not check it. But I hope basically it was clear. After this if we query we will get the reflection. I hope the code has been pretty straightforward and you have been able to translate it with the visuals and whatever we discussed. And also you are convinced that why all these operations are log n, and hence we can say that irrespective of how our update and sum operations are distributed in our Q queries, we know that the entire thing is going to be Q into log n. Make sense? Because our update and query both are actually log n in terms of the time complexity. So can we say that Q into log n is our total time complexity analysis? So what can we say from here? That n is the time taken to build the tree and then it is Q log n. So actually if the n value is a bit high, it is encouraged that you don't use n log n, those things basically. You don't use n different updates to form the build operation. Build operation can be replaced by n different updates. You will update each and every leaf nodes, but that will actually cause it to change from n to n log n. So if n is larger, if n is around 10 to the power 6 and q is around 10 to the power 5, and then n log n is a bit more expensive, or if you have this slightly greater. But anyway, I hope this makes sense, whatever we discussed till now. If any doubts, you can ask, else I think We can wrap up the things from here. Build is order n, and all the other query, whatever query or update is order log n per operation. Your recommendations from here to get into more details for more general use cases. Okay. More general use cases, I'll be discussing some of them. And apart from that, you will get questions if you're asking for that. You will get good content in Codeforce's blogs. You will have some good websites like CP Algorithms. You have CACS handbook. They all are good websites. You can actually cover them. So anyway, just to wrap up quickly, what are the things? What are the other things? Is there an iterative implementation also? What have we done differently? Okay, if you're talking about non-recursive, then that is not popular. We don't have any. I can't recall any kind of iterative implementation. In fact, this recursive one is so easy that we don't look at iterative implementations. We can always create, it's not a big deal, but it's not a very popular one. Okay. Now, which operations can we cover using this? Basically, when we have to update it, suppose this is the kind of update we are talking about, we'll go to an index and we'll change it. This is the only update. We can also say that, okay, at a certain position, I want you to increase it by a certain value. So this is my update operation, that at a certain index it will be increasing by a certain value. This is also the same thing. Just the update operation, the base case you have to change it. In this base case you just have to write it plus equals to val, and rest everything will be same. Over here also it will be exactly the same. This is one variation. What are the other variations? What is the operation? That okay, in this range now we have found out sum. What are the other things we can find out? Given that we have been told beforehand, these are the things we have to find out. So segment tree also will be forming in that manner. Suppose we want to find out the max over subarrays. Then we can actually find out max segment tree. What is this? Something like this, that every node tells us what is the maximum in this particular range. What is the maximum in its particular range? So what do we know? If we find out, if we need maximum from L dash to R dash, what can we say? Or from L to R, whatever you call it. Basically, if you have to find out from a certain L to R according to our example, if this is basically our, yeah. It's quite a large eraser. Anyway. So what can we say? This is an associative operation. If I tell you that there are three parts of LR, this is one part, this is another part, this is another part. Over here the maximum is x1, over here the maximum is x2, over here the maximum is x3. What can you say? If I have to find out the maximum over the entire thing, what do I need to do? Just find out the maximum of these three values. Does it make sense that I just have to find out the maximum of these three values and then I'm done with this max segment tree? Right? So this property is actually associative. In some segment tree also we have exploited the same property. What we said is that break it into different parts, find the answers of the different parts and then add them up. Sum is associative. That is why we are able to do it. The answer for one part plus the answer of other part is equal to the total answer. Even for maximum it is the same thing. Maximum of one part and maximum of the other part, if we find out the maximum of both of them, we'll get the final answer. So max of x1, x2, x3 is going to give us the final answer. Is this thing clear? Intuitively, can you understand what basically I've mentioned over here? Similar goes for min. Any doubts? And can you think of related operations where we can do exactly the same thing? Pour the doubts if you have any. So you can see over here max segment tree. This is one implementation I had done at some point of time. Upper right corner is your video, so can't be used for drawing. Thank you. Thank you. I never thought about it. Okay. Great Priyank. Even GCD works. But in case of GCD, can you think of something, Priyank? What will be different and everyone else? In case of GCD, What will be different from max segment tree, min segment tree, uh, sum segment tree, XOR segment tree, bitwise AND segment tree? All these are associative operations. Bitwise AND of this part, when we do bitwise AND with the bitwise AND of the other part, we'll get the total bitwise AND. So what will we do different in case of GCD? We will do GCD definitely. This merge operation, which I'm doing over here in terms of max, this we'll be writing GCD. But what will differ from these implementations? Think about time complexity maybe. Till then, let us cover this. So for maximum part, what am I doing? I'm just finding out this max. And that's the only different thing I'm doing. If it is matching, then I'll say, okay, this is the value that I have. Otherwise, what I'll say, fetch the maximum from your two children. That is your maximum. Whatever you get as a maximum, that is your maximum. And send it. Your parent is going to take care of it. Additional login, exactly. Very good. So update operation also we are doing in the same manner over here. I'm sorry, we are merging it. Rest everything is the same over here. Also we are actually doing equal to val, and everything else is the same. Query operation also, this particular part is different, else everything is the same. And for max segment tree, I'm returning 0. Why? I'm actually assuming that all the numbers are positive. That is why I'm returning 0, because I know that this will not influence my answer. The parts which are valid, they will influence my answer. So you have to take care of it. If there are negative integers, you should use integer.min value or whatever you have in your respective languages. Make sense? Cool. So for GCD, the thing is, we have to bear an extra log n. Why? Because this merging operation, this combining operation, that when we are joining two nodes, we have to find out the GCD over here, which is exactly equal to the GCD of this value and the GCD of this value. Whatever is the GCD for this node and the GCD for this node, we have to find the GCD of both the values, which means an extra log n factor. Not log n, basically we should say log of absolute value of AI. Make sense? Log of AI is going to be or we can say this is the maximum AI value. So log of that value, log of 10 to the power 9, we can say that part will get multiplied. Make sense? Okay, seems good. So if you have any questions, please do ask, else we'll move ahead. And we'll cover just the basic things, whatever coordinate compression and sparse segment trees I talked about. Tomorrow we'll be discussing all of them together with lazy propagation and many other things. So please revise these things by the next class, before the next class, because tomorrow's class is going to be quite advanced, and I'll be like, I will not spend too much time on all the details. We'll use similar intuitions so you can actually relate to it, but do make sure you revise all these things. Will it be n log n whole square for GCD? Okay, so it should be, since you're finding the GCD of two values, that value AI has got no relation with n. AI can go up to 10 to the power 9. So it will be basically 10 to the power 5. I'm sorry, n into log n whole square. Why n into log n whole square? I think q into log n whole square. So q is 10 to the power 5. Suppose n is also 10 to the power 5. So we have log of 10 to the power 5 for the queries. And for each GCD operation that we are doing in the path, we have extra log of 10 to the power 9. So not exactly 10 to the power 5 log of 10 to the power 5 whole square. It is different. Okay. This is actually coming from the AI value. What should we return instead of 0 for GCD? Very good question. For GCD, we actually have to be cautious. When we are calling something, we have to see, maybe we can return 0, and if we get 0 from over there, yeah, for 0, what do we know? That the other value is going to remain, right? For 0 and any other value, we know that the GCD is going to give 0. So we have to take care of it, that if 1 is 0, then the other value has to be kept. Either in the GCD function we can take care of it, but we can face errors. So, but 0 can be a safe value. We can keep over there. Make sense? Some part will be valid. Definitely, if you have visited a node, if you are visiting the children, some part will be non-zero. The other part can be 0. And we'll take just the other part. Clear? And Arnab, is it clear? Why not exactly log of n whole square? Why log of n into log of ai? Hope it is clear. If you have any other queries, you can ask. Okay, so now let us delve into our question. This is our second question, maybe for the day. Slightly more tricky, slightly trickier. I want to find basically every query, again, n numbers. AI is less than equal to, no, division is not associative, right? Especially integer division, that's not associative. We can't say that 5 divided by how can we break it? Yeah, 5 divided by 2 divided by 2. How should we actually show it? That's not associative. Anyway, you can actually figure out from this example. But anyway, suppose ai is less than equal to 10 to the power 9, 1 is less than equal to 10 to the power 1 is less than equal to less than equal to 10 to the power 9, n is less than equal to 10 to the power 5, and q is also less than equal to 10 to the power 5. There are q queries. Each query actually asks you that what is the count of maximum value, what is the count of maximum value in L to R. So L and R is less than equal to n, and there are that many queries. I want you not only to find out the maximum value, which you may or may not find out, I want you to find out the count of the maximum value. So coming right to the point, I want to make as less changes as possible in this segment tree. What is the different thing that I need to do? So one thing that you can understand is that this tree X contains my value. But also another thing is important, that when I know that a node is fully covered, I want to know that this maximum value is present how many times. So what are the things that I want to, that I should store in each of my nodes so that I can combine the values over all those nodes? Essentially, what do we want? Our structure tells us that eventually we'll be getting log n number of nodes which will be contributing to our answer, and we want to include their answers to form our final answer. This is our final answer. So now try to answer this, that what information should we try to combine from all these nodes? Exactly, very good. Store maximum and frequency in node. We will store the maximum value in a node. So every node should contain what is the maximum in that range and what is the frequency of maximum in that range. These are the two things. If I have that in all of these, I can combine them. How can I combine them? That's simple. I can just say that, okay, find out what is the maximum among all these nodes, and then whichever is the maximum, add their frequencies. Done, right? So if these are two nodes, over here I see that the maximum is 5, over here the maximum is 8. What can I say? That if the frequency is, suppose 3 over here, the frequency is 2 over here, this is not important to me. Only this part is important to me. Why? Because I know 8 does not exist over here. Because 8 is larger, 8 does not exist over here. Had this existed in this range, this would have been greater than 5. Right? So maybe in your free time you can think about it. Node is not operating in the same, mode. Mode is not operating in the same way. Mode means finding the highest frequency node. So if you have to find the highest frequency element, it does not operate in the same way. But in case of a maximum value, it actually provides this advantage. So that's it. How can we combine it? Now these three operations are left. We want to store these two things. The only thing that segment tree requires you to think is how can we combine, and then query and update will come automatically. That is not a big thing. That is not a big deal. So let us see if for this node I know that I have max 1, over here I have max 2, over here I have frequency f1, over here I have frequency f2. F1 is a frequency of max 1, f2 is a frequency of max 2. I want to find out what will be the value of max and f. How can I find out? Basically, exactly as Priyank has mentioned, if, and please ask doubts and please think deeply into it why I'm doing this. If max 1 is equal to max 2, what do I know? Can we just say if max 1 is equal to max 2, then max is equal to max 1, and f is going to be equal to f1 plus f2, right? If it is not the case, what can we say? Else if max 1 is greater, max 1 is greater than max 2, then what can we say? Max equals to max 1 and f equals to f1, and then else there is only one case left. No other magic can happen that none of them is greater, and they are not equal also. So basically, if it is not equal, then one of them has to be greater. So basically, max 2 will be greater than max 1 in this case. We will say that max equals to max 2 and f equals to f2. Is it making sense to all of you? Is it clear? Does this make sense? It's clear, right? All right, so let's move ahead. I hope it is clear to all of you. If you have any doubts, you can ask questions. So this is the only thing that I need to change. So what will I do over here? I can basically store two arrays. One is tree, another is tree1, or I can name them by tree max and tree frequency. And then both of them I can basically go on updating and querying whenever I require. I know that I basically know how to code down this merge operation, this merge function. I know how to do this. Not only this a and b are important to me, but I require basically maybe over there I'll have to send these two indices, 2x and 2x plus 1, and then I have to use those values to update it. That's it. Okay. So similar way, it's quite generic, right? Nothing too different. So moving along similar lines, let us solve a problem. Moving along similar lines, find the maximum. This is our last problem for the day. Try to do it yourself. Find the maximum sum of any segment L dash R dash inside LR. This is basically the query. So again, there are like u is equal to 10 to the power 5 or less than equal to 10 to the power 5 is exactly the same thing. N is less than equal to 10 to the power 5, and yeah, EI is also 10 to the power 9. So what am I asking? Basically, segment means a contiguous segment. So if this is an array 1, 3, 2, okay, minus 10 to the power 9, minus 10 to the power 9 to 10 to the power 9, okay, it can be negative. So 1, 3, 2, minus 5, minus 2, 6, minus 4, 3, minus 1. So over here, if I ask you what is going to be the maximum sum segment over here, you can tell me, or maybe over here, then you can tell me that this is the best segment. This is the next best segment, we can say, or maybe if I, yeah, this is the next best, and this would be the next best probably. I don't know, maybe 6 minus 4 plus 3, something like this. Got it? So basically, we have to choose that subarray which has the maximum sum. We have to print what is going to be the maximum sum of any subarray in this array, in this particular range, L to R. Got it? 1 less than equal to L less than equal to R less than equal to N. Again, think in the same terms. I hope the question is clear. Do we have to update query also? Yeah, exactly. I'm sorry if so you have to update. So position like A of pos equals to val. Similar way, this update operation is also there definitely. Else it is a very different sum, right? So yeah, all of you who are active till now, just tell me if you have understood the question, or is there any doubt in the question what I mean by segment, or what I mean by any segment. If there is any doubt, do clarify it. Else I'll be explicitly waiting for your answers for this question. Okay, great. So think about it and think only in that term. What can we store in every node? What can we store in every node such that query and update is easy? Query and update is easy. By now you have understood that they are easy if the merge operation is easy. So if the merge or combine operation is easy, then both are easy. The second thing is that it should suffice to give us the answer. Suffice to find final answer. The only difference with all the previous sums is that here finding the maximum sum is not like an associative operation. A segment can start from one node, it can end at some other node, right? So if these are two nodes which are contributing to your answer, it may happen that it starts over here and ends over here. So this is basically, yes, this is a subsegment, this is a segment of the previous node, but you cannot say that, okay, if this is the maximum segment, something over here, you cannot say that I'll take this maximum segment and I'll add that with that maximum segment, right? You cannot suddenly add these two things. So you cannot add two segments from anywhere because it has to be contiguous. So what can we store? What can we store inside each node? So that these two conditions are satisfied. Position. Okay, so in order to ask correctly the question, in the previous question, I was storing what? The max and the count value. So over here, what should I be storing? Start index, end index, and max sum. We are already storing that even in the simple max segmentary, right? That what is the okay, max sum, maybe max sum in segment. The problem is that suppose these are two nodes, and suppose the answer is such that it takes these values and it takes these values, but the maximum segment is something else. It is these values. This forms a maximum segment. I'll give you an example. Suppose this is one part which is minus 300 minus 4 minus 400, maybe minus 460. So these are four elements in one node, and this is another node where again it's a sort of symmetrical. 60 minus 400, 100, and minus 3. Okay, so consider over here, what is the maximum sum over here? 100. This is the maximum. You take any subarray, the best subarray is 100 itself. Take over here, this is the best subarray, 100. But taking both of them together, what is the best? Isn't it 60 plus 60? You cannot join 100 and 100 together. You cannot say that in this way we'll get 200. They have to be contiguous. So in this example, we should basically take 60 plus 60. But this will tell us that, okay, my maximum is 100. It will tell my maximum is 100. So it will lead us to the wrong analysis, because it will not at all take into consideration what is there at the terminal ends, which may help in extending the answer, taking into consideration the other nodes. Yeah. What about the rest? Is that sufficient? Raid Singh, is that sufficient? And what about the rest? What do you think about this thing that he has mentioned? Because today we have done pretty basic things, but on these basic things, many complicated questions can be formed, and this is one of the classical versions of it. This is what we are looking forward to do. So what can we store in every node? I hope my counter example was like intuitive. If we just store max prefix sum, how about update? Nobody is actually forcing you to store one value. Over there I was storing the max as well as the count, right? In the previous example I was storing both the max and the count. So over here also you can store multiple values. But whatever you store, it should be easy to update. That is important. It should be easy to update. It should be easy to query also. Query means during querying it should be easy to add two values. So the value should be such, and you should be able to find this final answer. Prefix sum, only prefix sum and its length. Okay. What about the rest? Like, this is not at all a very complicated problem, so I would encourage all of you to stick to it a bit. If you understand this, probably after this many different sums you'll be able to do by yourself. Think about these 4 arrays. What I'm telling you is, I want to find out what is the best sub-array over here. What information can I store here so that I don't have to visit their children explicitly? I know that all of them are fully involved. Or for convenience, just consider 2 different nodes currently. Just consider that you have 2 different nodes. What can you store so that you can join them pretty easily over here? What values can you store? Prefix sum and suffix sum and their length. Okay. So then, suppose this array contains something like this. Instead of 100, I had 200 over here. 200 and minus 460. Won't I be losing this? And over here I have 60 minus 400, 200 and something else, minus 3. Won't I now be losing this? If I just take the suffix, if I just take the prefix, if I don't take these middle things, won't I be losing these values? Because now 200 is the answer, right? Can you see the case? Can you visualize the cases? What can occur? How my segments can go, how they can involve multiple nodes. If multiple nodes are involved, how they might involve them. Because it is a subarray, it's not that randomly you pick up elements from here and there. So there is a pattern, you just have to catch the pattern. Middle maximum also, okay. So I'm mentioning 3 things. Prefix sum, suffix sum, and middle max. Okay. Cool. Is this sufficient? Yes or no? Please mention in the chat. There is no harm in writing anything wrong. No one is going to judge you based on your answers, but this is important. Is this sufficient or not? Because in contest, this is what will decide whether you can completely solve this question or not. Structure of the segment tree, every programmer knows. how to utilize it, that is what makes the difference in your performances. Just write down, do you think it is sufficient or not? Okay. For sufficiency, there was only that single thing that I mentioned, or maybe two things. But the primary thing is, can we join the two things? So let us say we have these three values, P1, S1. P1 is a prefix, S1 is a suffix, and M1 is the maximum in this part. Over here, the prefix is P2, suffix is S2. This is the maximum. What will be P? What will be P? We have to find out the prefix, the maximum prefix for this particular range, right? Which involves both these parts. So what is P? Any guesses? Can we write P in terms of P1 and P2, or P1 S1, P2 S2, M1 M2? Can we write? If we can write, what can be the relation? If we cannot write, what is the reason? P equals to P1, okay? What if I say that this is 560? What if I say that this is 560 instead of 60? Then can we say that this should have been our P1? This particular summation should have been our P1? Minus 3 plus 200 plus minus 400 plus 60 plus 560, right? Shouldn't this have been the P? So can we say this is a case where P is not equal to P1? Yes or no? Max of S1 comma S2, S is the maximum, S is the suffix, S is a suffix, if you have understood it correctly. S is the suffix. So, okay, if it does not cover, then? If it does not cover, then? M1 plus N2, again you're making a mistake. Why, or maybe you meant M1 plus P2, but whatever it is, M1 is somewhere, maybe it is lying somewhere in between. You cannot suddenly join it with something of the second array. M1 is basically something that is lying in between. It is the mid. So suddenly you cannot say that join it with something else. And M1 cannot be the max. I'm asking, like, what is the prefix? What is the best prefix for this entire range? So there are two cases if you analyze it. The suffixes are not at all important. I'm not interested in what is the suffix over here, what is the suffix over, maybe the best suffix is over here and the best prefix is over here. So by adding the suffix, what will you find out? Let's say I do what you are telling, S1 plus P2. S1 plus P2 means what? This is S1 and this is P2, right? This is P2. So is this a prefix of this array? Right, exactly. Very good. P1 comma sum1 plus P2. So we need another attribute which is sum. Sum of this entire node. So we know that our prefix is going to be either a prefix completely in A, completely in the left part, or it should be a prefix of the right part plus the total thing of left part. What I just mentioned is prefix equals to either a prefix of left part, in which we can say that P1 is our answer, prefix of left part, or we can say that it is total of left plus prefix of right part. The question is, why, like, would you require it? Right part. You can store it, and maybe had I got some time I would have delved into detail of each of them, but the question is whether, like, can you really store it, like, or not, can you really, like, should you really store it? Does this give you any advantage, so that we can derive if it covers? Okay, suppose you see that it does not cover, what is your gain? You are saying that, okay, if it returns true that yes it covers, then I'll get total left from there. If it does not cover, then can we say that we don't require it? We may require it. So do I get some extra information? No, that is only solving a particular case. I have to solve for all cases. And for all cases, keeping all cases in mind, I need something to store the total which is there in the left. I hope you can understand these two things. I'm saying either this case or this case, whichever is the maximum, right? So coming back to where we were. These are the four things that we have decided to store. We can find out P. Can we find out S? Yes. Again, S2 and total of whatever the total is, total of 1 plus, total of 2 plus S of 1, the maximum will be our answer. And next we can say that, okay, if you are looking for the mid, what is the mid? What can the mid be? What will be the summation? Summation will be sum of this plus sum of that. So total plus total. So we can say T equals to T1 plus T2. So we will say that this is the total sum, right? So T equals to T1 plus T2. Now the only thing is how to combine the middle part. How to combine the mid max. It may not be in the mid, it may be in the terminal, but what I want is it should be contiguous anywhere inside the array. So mid max, let us refer that as capital M. So capital M is equal to what? First of all, I know it can be M1. I know it can be M2 also. But it can also happen that it starts in 1 and ends in 2. And what is the best case for it? Can we say that the best case is a suffix of 1 plus a prefix of 2? To be more precise, the best suffix of 1 and the best prefix of 2. And other cases I've already considered that, okay, I may choose it explicitly from a particular part, either from left or from right, or we will combine it. This is the combination. So if it is there totally in the left part, my left part should be able to give me. If it is there in the right part, my right part should be able to give me. If it is there belonging to both the parts, starting from one, ending at the other, that means the part which is lying in the left part must be the suffix of the left part. And can M1? Definitely, it can cover. M1 we are not doing any kind of partiality. If at any node we see that S1 covers the entire left guy, P2 covers the entire right guy, we are going to take it. We are going to take S1 plus P2 equals to the entire thing. And M1 will contain, or M will contain the entire sum. M will be equal to T in that case. M will be equal to T in that case. Should S1 be a proper suffix? Not required. It can cover entire segment. It can cover entire segment. We are interested in the prefix. So there is no advantage by preventing one particular case. We can verify that without that also. Maybe if we skip that one case, maybe our answers can be in our favor. We can get the answers easily, but that will be difficult to implement and unnecessarily a problem. But this does not give you any counter example. Prefix means prefix, suffix means suffix. Prefix plus, total plus prefix means again a prefix of the concatenated one. Suffix plus total means a suffix of the concatenated one. So the definitions are fine. Keep it simple, they may overlap. You may get that, okay, my answer exists in both capital M as well as small s. Maybe my answer lies in both of them. Not a problem. At least one should have the answer. If 2, 3 values have the answer, that is not a problem. We'll take the maximum. Okay, any questions? Suppose the question has that at least one element should be taken. If any one element is to be taken, then while you're combining it or while you're starting this calculation of M, make sure that if it is negative, then also it stores the negative value. It does not store 0. Okay. Solution can be through few segments too. Exactly, like few segments means how many segments? It is basic range operation. the way you did range sum, you are going to do exactly that way. So from 0 to 7, you had your nodes. Suppose I tell you, okay, find out from 4 to 6. So what will you say? Okay, find out from 4 to 5. You will get one node and then combine it with 6 to 6. That's it. There can be multiple, but the analysis, the progression, the segmentary function is exactly the same as we had in sum segmentary. Suffix, entire, prefix, for example. Okay, suffix, entire, prefix, for example, I didn't quite get, but anyway. Yeah, okay, solutions, yeah, they involve multiple cases. So what basically Marijan is pointing out is something like this. So suppose we have these nodes. So what is happening, they may have to be combined. If they are combined, what will happen? First, some two will be combined. पहले दो combined होंगे, first any two, then these two may be combined, and then maybe these two are combined. Something like this will happen. So whenever you are combining, there will be in terms of two. Then when you are forming it over here, this is again going to have your four values, and when you are having over this also has your four values. So again you have basically four sets of pairs, and you have to merge them to form this final thing. And then what is the answer? Final m. Not it? That's it. So okay, it was quite a long class, one of my longest classes till date. So if you have any questions, and by the way, in segment 3 again, if something is left, I won't be hurrying tomorrow. I'll be extending it in the last class, which is preserved though for problem solving, but we can do it hand in hand. Segment 3 implementation needs to be 0 based index or 1. It is up to you. Over here I have done 1 based indexing. You can see I have done 1 based indexing. Why? Because the transition was easier. From okay, over here you can see from 1 I had 2 and 3, from 2 I had 4 and 5. So you can see that I'm just doubling and then adding 1. So that is why 1 based indexing has helped me over here. But you can have any base. If it is 0 and then 1 2 and then below 1 you have 3 4, you basically have to do something like 2x plus 1 and 2x plus 2. In case of 0 based indexing, you need x and 2x plus 1 in the left side and 2x plus 2 in the right side, I guess. 0 1 2 3 4 5 6, yeah, turns out to be so. Okay. Okay, folks, if you have anything to ask, you can ask. I've put a lot of energy. Now it depends on you how much practice you put in. Expecting that tomorrow you all will be coming with by revising all these things, because tomorrow we'll be having fun with a lot of more intricate things. Of course, you can ask doubts from whatever we covered today, else we'll see more fascinating things around this topic. Thank you. Have a nice evening. Take care. Keep coding. Last 1 minute I'll be staying. If you have any doubts, you can ask. Else we'll be calling it a day. Oh, okay. I see the image is quite big and I can't do. Okay, I can shift it. But anyway, it will hamper me somewhere or the other. That's right. What all we need to brush up for tomorrow? Whatever I discussed around segment trees. I've discussed basic segment trees and these operations. Whatever time complexity analysis I've done it basically in detail. I've explained why they are log n in nature. So you can go through those proofs. You'll actually find the proof of the next parts also very relevant. Okay. You won't actually require extra effort if you are good with this proof. Cool. Take care. Keep coding. Bye.